Hi friends, so let's start our lecture 62 on the helicopter dynamics course, and today I'm going to discuss one more method for solving periodic differential equations, and today we are also going to account for nonlinear terms being present on the right hand side, that is in the force vector, and this method is known as the FEM in time method. I am Dr. Ranjan Ganguly. Now we have seen that after all the shenanigans and mathematical manipulations which we do, we end up with differential equations of the form mq double dot plus cq dot plus kq equals f for typical dynamical systems, such as the helicopter rotor in forward flight. Now, what we are going to do to solve this equation is we are going to consider a time-based discretization of the solution. So we are going to use basis functions in time in a manner very similar to how basis functions in space domain are used in the classical FEM method. We are also going to impose periodicity on the solution as a boundary condition in time. So consider the matrix differential equation of this form: mq double dot plus cq dot plus kq is f. And as before, m, c, and k are periodic functions of time. For example, they may contain sinusoidal terms and so on. And also there may exist nonlinear terms, and all these nonlinear terms are moved to the right hand side into the force vector. So remember that if there are any linear motion dependent terms involving q double dot, q dot, or q, they are all moved to the left hand side of the equation, and so what's left on the right hand side are the nonlinear terms. So we can consider f to be a periodic function of time, which is a function of psi, which is the non-dimensional time. Also it can be a function of q, q dot, and so on. Now what we do here is we take the differential equation and we create something which is known as the weak form. So essentially the differential equation must be zero at all points in the domain. So what we do is that we multiply it by a variational delta q transpose, and we say that the integral of this value from 0 to 2 pi is equal to 0, that is across the domain of this problem, which is 0 to 2 pi. Okay, now here what we do is we are going to reduce this mq double dot term by integration by parts, and that's done as follows here. So we take this function and we simplify it in this form. So we take the first function into integral of second minus integral of differential coefficient of the first function being delta qtm, into the integral of second. Okay, remember the integration by parts formula. Then we expand this out and we get this form here. So what we achieved by integration by parts is that we got rid of the q double dot term and we expressed it in the form of the q dot terms. Okay, and we also moved certain parts to the right hand side, and this part becomes 0 because we can impose the condition that these particular quantities are periodic and therefore they're going to be equal at 0 and 2 pi, and therefore this part is going to vanish. So now we have this equation here. We can express it in the form given here, and then the right hand side becomes 0 because m, q dot are periodic over period 2 pi. Now if you look carefully here, we split this into delta q and delta q dot. All these terms are delta q terms except one term which involves delta q dot, and the delta q dot is the term which involves mq dot here. So the mq dot has come here and there is a 0 here, and all the q terms have come here. So there is a negative f, there is a cq dot, there is a kq, and there is a negative m dot q dot here. So that's how we get this equation. We set the right hand side to 0 and we can write this in a simpler form. delta yt q d psi equals 0, where this is my y vector and this big matrix type of term here, which is actually expressed in this form here. So that's what we get at this point. Now we look at this equation. This has two components. This has y, which contains q and q dot, and it's got q, which contains f, c, k, m, q dot, m dot, and so on. Now what we do is we discretize this integral into a large number of parts. So let us say we have several time elements, any of them specifically. Then we integrate i's 1 to ne, and we break this integral up from psi I to psi I plus 1, and then we have all these values within this particular segment I here, and this should also be equal to 0. So this is how the rotor is divided up. Essentially, each of this is the segment number I, and each of this is then partitioned into psi I, psi 2, all the way to psi n plus 1, and psi is going like this here. So the rotor disk is partitioned into a number of FEs in time. Now psi 1 is 0, and at the end of the disk psi ne plus 1 is 2 pi. That's where the rotor disk ends, and there are ne number of time FEs. Now we take a Taylor series expansion of q round the steady state value y0. So this is some value q0 q dot 0, and we expand it about this value, so we get something like this. So now this is expanded out, and so what you get is you get a vector and you get a matrix into a delta y. So this particular matrix is known as the tangential stiffness matrix, and you can express it as follows. This matrix is very interesting. It contains mck, but it also contains the derivative of f with respect to q and f with respect to q dot. So you can think of this f with respect to q as a kind of tangential stiffness, and this as a kind of tangential damping. So in general, when your FEM in time is progressing, the stiffness and damping keep changing due to the derivative terms involving the force vector, which are coming because of the presence of nonlinear terms. So of course, if your F was completely non-motion dependent, then these would be 0. And remember, if they were just linear functions, they would have moved to the left hand side and been part of K and C. So this only happens because of the presence of nonlinear terms on the right hand side in the force vector. So if you are at the I number Fe, then the displacement vector q is now expressed as follows. So this is the fundamental step we do here, is that we are expressing the displacement in terms of shape functions, which are functions of time. So that's the big thinking behind FEM in time, and these xi i's are going to be the nodes. So that's how it looks like. S is 0 to S is I, and S is basically time within this particular FE. So this is defined as psi minus psi I by psi I plus 1 minus psi I, and S you can see varies from 0 to 1. So when psi will be equal to I plus 1, this is going to be 1, and when psi is going to be psi I, this is going to be 0. So these are the two ends of the FE here, and time is varying within this particular segment. So that's a major step, that we can express q as a function of time here and then bring out these nodal coordinates I. So psi I plus 1 minus psi I is the time span, or it is the length of the FE number I. Now corresponding to this, there will be a polynomial within each of these segments, and so nt is the degree of this particular polynomial, and this approximates the temporal variation of the nodal displacement vector. Temporal is just one more word of expressing time. So if we have a nth degree polynomial, then the nt plus 1 nodes are needed to describe the variation of q psi. For example, if I have a fifth degree polynomial, 6 nodes are going to be needed, and typically we can use Lagrange polynomials in this problem to expand this function out. So this is the typical fifth degree polynomial which is going to be fit on the 6-noded FEM. So here you can see there are 2 end nodes, there are 4 internal nodes, and so nt is 5 and there are 6 nodes in this problem. So these are the shape functions corresponding to the particular model we have developed, and you can clearly see that these are essentially polynomial. The maximum degree is S5 and then there are the remaining values here. So essentially it's very interesting that we have been able to split time into a polynomial form. So now that we have this expression of q in terms of these shape functions, we can quickly obtain q dot by differentiating the shape function. We can obtain delta q and delta q dot by again differentiating the shape function and then taking the variations in each case. So these variations are taken on the nodal coordinate. So put these in the starting matrix equation, we get this here, and now what we have done is, remember again, y is q dot, and so yi can be represented in terms of h and h dot, which we now call as n. So that is a new nomenclature. We combine both these two, and yi is n psi I, and then I go and substitute this in the main differential equation, or the main equation at this time, because the differentiability has been actually wiped out by taking this particular time variation. So again we take the variation values here, we substitute this here again, and now as you can see we have expressed all the things in terms of the nodal coordinate, and now we have n, which is the shape function, we have the q, the load, and we have the tangential matrix. So you can then assemble these equations just like we do it in the spatial domain, and then the equation essentially becomes a system of this form: qg plus ktg delta psi g is 0, and since we know qg and ktg, we can solve for psi of g, and we have to keep doing this process because of the nonlinear nature of the system. So these are some of the details here. This is the global equation here, and this global equation is obtained by putting together the q and the k expressions in terms of these particular vectors and matrices. So you can see here that I essentially need to bring in the shape functions here. Recall that n includes the shape functions h and h dot, and once I have it, I can put together these matrices and vectors and solve this problem. And I also get the global displacement vector. So finally we need to apply the boundary condition, and the boundary condition in this case is that q0 equals q2 pi. Okay, that means at this point 0, you go around the whole thing and you are back at 2 pi. So essentially the nodal coordinate here has to be made exactly same as the nodal coordinate coming from this side. So that is a constraint you need to impose on this problem, that these two nodal coordinates are exactly same, and once you impose that, periodicity has been brought into this problem. So now to start the iterative process, we initially do not know the response of the system, that is, we do not know the y vector. So if you had some good value of the y vector, you could take it, but in general we don't. So we take the initial guess to be 0, and that generally works out quite well for this problem. So you continue doing this particular procedure. So as you do it, after some time you will converge. This is quite fast in terms of convergence for moderately nonlinear problems which you typically find in helicopter dynamics and rotor dynamics. And this method can be used on some other type of systems also which involve periodic differential equations, so don't need to limit yourself to only the helicopter dynamics problems. If you are a mathematical person facing any kind of periodic differential equation, you can go ahead and use the FEM in time, and please let me know how it has done, or you can go ahead and publish papers on that topic. So today we looked at this particular method of solving periodic differential equations. Governing equations being nonlinear, this method works out very well. You keep using this method till you converge, and during the process, if you are working on a helicopter dynamic model, you put something known as trim controls, which are essentially theta 0, theta 1c, theta 1s, and the vehicle orientation in space at that particular time. Now, you can keep changing those also while your response solution is going on. So there is essentially a system of two nonlinear equations moving ahead at the same time in typical rotor dynamics. One is known as the trim problem, which we will discuss later in this course. That's actually all the forces which act on the helicopter system must come up to zero. And the second is the response solution which is going on. So in some cases, these two things are combined, and that is known as the coupled trim solution. So you will hear that many comprehensive aeroelastic codes, they are using coupled trim, and essentially what they are doing is they are solving the trim equation simultaneously with the equations for the rotor blade. And so when you do that, you get very quick or reasonably quick solutions for the problem. In most of the cases, coupled trim gets slowed down because of the use of free wake. If you are not using a free wake, it's generally quite fast. So I will stop this video here, and I will see you in my next lecture.